only difference is that now concrete has cracked and stresses are not taken by the concrete because concrete section is already a cracked section. So this stress portion taken by the concrete will disappear. You will have only tensile stresses in steel, and there will be no tensile stresses in concrete. Concrete is not able to resist any tensile stresses because it has already cracked. So you have compression stresses in concrete and tensile stresses in steel at that particular instant. Okay, so your tensile strain in concrete is now equal to the cracking strain. Your tensile strain in steel is still less than its yielding strain, and compression stresses in compression strain in concrete are still less than the proportionality limit strain of that particular concrete. So they are in linear elastic behavior, and you can still use Hooke's law to calculate your stresses using these strains. So first of all, the moment at that particular instant is actually the cracking moment because your tensile strain in concrete is equal to the strain at the cracking strain. So the moment occurring at that particular instant is actually the cracking moment. Uh, so that is actually the tensile strength of that concrete, or the tensile stress occurring at that particular instant in concrete is actually tensile or strength, which actually a flexural strength because beam is loaded in flexure or bending. So you can calculate it using this equation from ACI code, which is 7.5 into under root F dash C. F dash C is the compressive strength of concrete. So if you get FR, you can now use the flexural formula, which is My or I. You can calculate your Y. For that, you have to first calculate your C, which is um, the location of the neutral axis. So you can again use the same transformed area or force equilibrium method to calculate C. Once C is calculated, you can calculate Y, you can calculate I, you already have got your um, FR, so you can easily calculate your cracking moment. So in a solved example, we'll see how we have to calculate the cracking moment, a moment at which the section just cracks, or crack is initiated in the tensile concrete, or the concrete which is in tension, which is below the neutral axis of that section. Then coming to stage 3, which is a bit more important compared to stage 1 and stage 2. Concrete has already cracked. Um, Section is still behaving in linear elastic manner. Uh, this is the same figure. Over here, there are no, because now there are no tensile stresses in concrete. So you have only tensile compression forces in concrete, and then tensile forces in steel. Your tension strain or tensile strain in concrete is greater than the cracking strain. So concrete section has already cracked. Your tensile strains in steel are less than its yielding strain. It is still in its linear elastic region, and compression strain in concrete is still less than the proportionality limit strain in that particular concrete. They are still in linear elastic region. So you can again use Hooke's law to calculate the stresses by multiplying these strains by their modulus of elasticity. There is some moment applied to that section at that particular instant because of the loads applied. So you can again similar procedure. You have to locate your neutral axis, calculate the value of C by using transformed area method or your force equilibrium method, and then you can calculate your moment, um, stresses strain by the using flexural formula and moment equilibrium. So for moment equilibrium, you can take moment at, because in previous stages you had tensile stresses in concrete as well. If you want to take the moment at this particular point from where this resultant of compression force is passing, you have to consider tensile stresses in concrete as well as tensile stresses in steel. But over here you have only one force which is at only one particular instant. If you take summation of moment at this sorry, I'm going to, okay, so if you want to take summation of moment at this particular point, which is basically the point from where your compression resultant of compression force is passing, you can take moment at this point. um your summation of moment equal to 0. So there is only one force other than this cc, which is ts. So ts into z, which is uh, the distance of this tensile force from this point. So you can calculate this moment, or in another way you can take summation of moment at this point, and your cc into z is actually your moment capacity. So you can they both will be equal. Compression force in concrete multiplied by this moment arm, or tensile force in concrete multiplied by this moment arm, it will be the same, and that will be the moment occurring in that section at that particular instant. So we'll be doing it in our solved examples. Then the last and the most important stage, which is stage 4. Uh, Over here we have again same section, width B, total depth of H. This is the strain profile, but now our stress profile has changed a bit. It is not varying linearly like the previous stages. The distribution is parabolic. So we have a lower compression stresses in the top fiber, then they increase, and then they start to increase till our neutral axis. Um, our tensile strain in concrete is greater than the cracking strain. Concrete section has already cracked. We'll not consider it for our tensile stresses because it cannot take any tensile stress. Tensile strain in steel is now greater than the yielding strain, as we discussed in our moment curvature graph, that steel has already started to yield, and it is a lot greater than its yielding strain. We'll discuss it in our examples as well, and we are assuming that it is a lot greater than the tensile strains in the steel for some particular um, reasons, because we want the section to be tension control, but we'll discuss it in our coming lectures. And now your compression strain in concrete, that has reached the ultimate strain in concrete, maximum strain which it can take, and as per ACI code we have to take the maximum value of 0.003. In previous lecture, we discussed that the ultimate strain for concrete ranges from 0.003 to 0.004, but as per ACI code, we cannot take it greater than 0.003. So we have to take it 0.003. Right now, our materials are behaving in non-linear manner So we cannot use Hooke's law to calculate our stresses by multiplying their modulus of elasticity. The moment at that instant is now the maximum moment capacity of that section, or nominal moment capacity of that section. We have again a distance between these resultant of this tension force and compression force. This is equal to Z. um, Analysis procedure is similar. We have to calculate, first calculate C, which is the location of our neutral axis, by taking force equilibrium method. um, tension force in steel is equal to compression force in concrete. um, as we already assumed that steel yields, so this is our assumption. And then we'll not be using uh, this stress profile, which is quite complicated one, because the distribution is parabolic. There is another distribution which is called Whitney stress distribution, or Whitney's rectangular stress distribution, which is similar to, like, this is the stress profile you have. This stress profile is actually converted into rectangular distribution. So we have, like, this one. Over here we have the maximum value of f dash c at this point, but now this maximum, or this dimension of this rectangular distribution, is 0.85 f dash c. But and this distance from this value is actually a. I'm not able to write it, but it is a, which is different than this c. It is actually a is equal to beta 1 c. We'll discuss it in our coming slides, but we will use this type of distribution to calculate our to locate our neutral axis. This is easier to use because it is a simple rectangular distribution. Calculating resultant and solving parabolic distribution is a lot complicated compared to this rectangular distribution. So I will be using this Whitney's rectangular stress distribution to calculate or to locate our neutral axis. And then we can again use the same equation, which is Mn is equal to tension force in steel multiplied by its moment arm, or compression force in concrete multiplied by its moment arm. So this was actually the explanation to the behavior of reinforced concrete beam, how it behaves when loads are applied to it, and there are bending stresses produced in the reinforced concrete beam. Basically, summarizing it, we have four stages. In stage one, when load increases, your curvature increases in a linear manner, and there is a point where concrete just start to crack. That is called cracking moment. Then again the loads are transferred to the um, steel, or basically stresses are tensile stresses are transferred to the steel. It again starts to increase in a linear manner, and then a point is reached where tensile stresses in steel reach a point where steel starts to yield again. But again there is an increase in um, moment capacity, and again we reach the maximum moment capacity of that section, which is Mn, nominal moment capacity, and your beam fails. So this is the general behavior of reinforced concrete beam. We'll be solving some examples in our coming lectures, and you will have a better view of how you have to deal with these kind of problems. I thank you for your cooperation, and if there are any problems related to this lecture or previous lecture, you can always contact me to clarify them, because don't carry your doubts with you. If you have some doubt at this point, it will create problems for you in our coming lectures. So you have to clear your mind, concentrate on your lectures, uh, clarify each and every point. Do not leave any single point. If you have got any doubt, you can contact me anytime. uh, I thank you, and best of